Thank you, Gary. I'm excited to be here and to get us started. I introduced myself briefly, but I'm Benjamin Pitt. I'm a postdoc at UC Berkeley, with working mostly with Steve Piantadosi. And I am going to share some recent data on the Tsimane, a group of unindustrialized people that live in the Bolivian Amazon. This is work in collaboration with Ted Gibson at MIT, looking at the role of language in the development of number concepts. So we already know from studies of babies and non-human animals that you don't need language for at least some numeric abilities. You don't need language to reason about small numbers exactly, up to about 4. And you don't need language to reason about larger numbers, but only approximately, using an approximate number system, as it's called. So the controversy really has been about the origins and development of large exact number concepts, meaning integers larger than about 4. So on one account, what I'm going to call the linguistic scaffolding account, this ability to represent large exact numbers depends on language. Specifically, the ability to master a verbal count list like 1, 2, 3, 4, etc. As Susan Carey said, these words serve as placeholders that are filled in with richer and richer meanings. On an alternative account, what I'll call a nativist account, large exact number concepts are innate. They're innately available. As Butterworth and colleagues say, we are born with the capacity to represent exact numerosities. And I won't get into the details here of how they think this is possible, but just to briefly preview that they have this accumulator model that involves a bunch of innate components that people can use to generate representations of any exact quantity. So importantly, though, the claim there is that there is no central functional role for language in these concepts. In fact, if anything, they say the opposite, right? They say conceptual development drives the acquisition of counting words rather than the other way around. So that's positing a causal arrow that goes in this direction from conceptual development to linguistic abilities. So there have been previous attempts to answer this question. You may already be aware. I'll just mention them briefly. In the Piraha of the Amazon and the Munduruku also of the Amazon, both unindustrialized groups and in a small group of Nicaraguan home signers, these groups have no words for large exact numbers and don't seem to be able to represent large sets larger than about 4. And so on the basis of those findings, people have concluded these findings seem to be evidence for linguistic scaffolding account. But I'm gonna, as other people have pointed out, there's actually these studies leave some room for legitimate skepticism. So as Gelman and Butterworth point out, each indigenous culture differs from Western culture in innumerable ways. It remains possible that one or more of these many differences were responsible for the differences in performance on these nonverbal numerical tasks, and not just the lack of counting vocabulary, right? And other people I've offered similar skepticism, which is just to say, right, that sure, there's this sort of cross-cultural correlation, let's say, between cultures that have no counting abilities and don't seem to be able to represent these large exact sets, but that could be epiphenomenal. There are lots of differences across these cultures, right? So just to make that explicit, right? Here are the 3 cultures that have been studied, and they're all at one extreme, right? Where there's no words for large exact numbers, and they seem to have no ability to represent large sets, and sort of implicitly we're comparing them to weird cultures, Western educated, industrialized, rich, democratic cultures like ours, where we're at the other extreme, where we're very good at counting and sort of have indefinite abilities unlimited abilities to represent large exact sets. And so there's this sort of implicit cross-cultural comparison. And that's, of course, fraught. So ideally what you'd want to do, and what we're going to do, what I'm going to show you here, is to look within a single culture, a single language group, and look at individual differences in people's verbal mastery of the verbal count list, and see how that corresponds to their ability to represent specific quantities. So that's what the Tsimane provide. Here's some images of my trip to Bolivia last summer. There's a lot that's interesting about the Tsimane, but for our purposes here, the critical thing is that unlike these other industrialized groups, the Tsimane do have a full counting system, right? They work, it's base 10, it works just very similar to the counting system in English, but they vary in how well they've mastered it. So there are some people who can count indefinitely, just like you or I, and some people who aren't sure what number comes after 7 or after 15 or so forth. And so what we did here is basically leverage that variation across individuals, often individuals living in the same small communities, all of whom speak the same language and have a shared culture. Leverage that variability in their verbal counting abilities and see how that corresponds to their ability to represent large sets on these nonverbal number tasks that I'll explain. Right, so our large exact number representation is limited to people's knowledge of the verbal count list. We can ask that question on an individual basis here without crossing cultures. Okay, so the way we did that is first we figured out how high people could count. We gave them a set of pebbles and asked them to count them out loud and saw where they faltered. And then we gave them these two nonverbal numerical matching tasks that are adopted from studies of the Piraha, where you present a set of n objects in the sample. So here's a sample of 5. And in the parallel matching task, the subject's job is to simply make a set of the same size, and they can do that by matching 1 spoon, in this case, 3 minutes, got it, 1 spoon to each of the keys presented. And then in the critical task here is the orthogonal match task, and it's exactly the same, except here, because of the spatial arrangement of the sample and the response, you can't do one-to-one matching. You have to, in order to get this right, you have to actually represent the cardinality of the full set. And so the question is, how well can people do that? Here's just a little preview of what that looks like. So here's the participant on the left. That's our translator, Elias, on the right. I've set up a set of 8 white buttons that you can see there, sort of away from the participant. And his job is to make a set of the same number, the exact same number, orthogonally. And he's just put 9 down instead of 8. So the question then is, okay, so he got that wrong. Well, he did a bunch of these trials, right? We used a staircasing procedure to figure out where they fail. The question is, how do we quantify someone's largest numerical match on this task, right? Is it getting it wrong 3 times? Is it getting it wrong by 2? Is it what? So rather than come up with sort of an arbitrary criterion, we used a generative Bayesian model here to estimate the number at which people are switching from an exact system to an approximate system. So there's some point at which people are going from being able to do exactly this set to approximating, and based on their pattern of errors, we can estimate where that switch point is. What is the set size at which they're switching? And then compare that switch point to their highest verbal count. And so just quickly, I want to run through the 3 different predictions that these 3 accounts make. On the nativist account, right, people should be able to do any of these things, that their verbal counting ability shouldn't actually matter. And in that case, all of their points should be above the line here. People should be above the diagonal line. On the epiphenomenal account, these 2 abilities might be correlated, but there's no reason to believe that one should sort of lead the other. And so you should find them roughly correlated. And only in the linguistic scaffolding account do you predict that actually all these points, all these participants should be below this diagonal line. Why? Because they shouldn't be able to make reliable numerical matches beyond their verbal count range. Their verbal count range should place a hard upper bound on what they're able to represent. So here's the data, here's what we find. And as you can see, almost without exception, these data points lie at or below the line. Okay, I'm running out of time, but I'm nearly done. And so what I've been showing you is low counters. These are all unread. Those are people who whose highest verbal counts are below 20, but we can actually, and those results stand on their own. We don't actually need to compare them, but we can compare them to a group of, a control group of high counters, also Tsimane people, but who can count, whose highest verbal count exceeds 40. Those are shown here in blue, and as you can see, they perform very well at this task. Their estimated switch points are well into the 20s, whereas no one in the low counting group exceeded 15 in their highest numerical match. And then actually, and finally here, I'm showing the probability that each of these low counters had a switch point that exceeded their highest verbal count, right? And what you can see is these probabilities are very low. What that means is that people were extremely unlikely to be able to reliably match the set of things, the number of things, if that number was beyond their verbal count range. So, and I just want to note that unlike this differs in a few ways from previous findings, but one important way is that unlike the Piraha and these other groups, the Tsimane participants are representing a large exact number, right? It's not that they're not doing it at all. They are doing it for small sets, but being able to do it for small sets doesn't get you the ability to do it for larger sets, right? That ability appears to be limited by your verbal counting abilities. So these results argue against the nativist account. They and provide support for this linguistic scaffolding account, and suggest something that was sort of awkwardly put by Benjamin Lee Whorf in 1956, that perhaps some concepts are not given in substantially the same form by experience to all men, but depend upon the nature of the language or languages through the use of which they have been developed. Yeah, so I'm out of time, so I'm gonna leave it there. Thanks to the Tsimane, first of all, to our translators, and to my advisors on this. So I think we have a couple minutes for questions. I'm at 12 minutes by my clock.
Great, thanks, Ben.
I don't know if I can call on people or if people just—
I got a question.
Yeah, please.
So, one can imagine that somebody understands the concept, but in the lack of the ability to reliably produce a count sequence, they wouldn't be able to execute the task. And that starts to get extremely plausible when you get into the range where, you have to accurately count the first set, and then you have to, keep the result in mind, and then you have to accurately count as you're going along and placing down the answer. And so it doesn't really speak to the question of whether they kind of basically understand whether they're supposed to kind of put exactly the same number down or not, which was what the question was, I thought, in the first instance. So can you tell us what you think about that?
Yeah, so I think, first of all, I think it's important to distinguish between having sort of some concept of exactness, right, of exact numerical quantity, that like there is such a thing as numerical equality. I think it's important to distinguish that from like having some representation of 8 or of 17, right? And so the question that I'm asking here is the latter, is like, is there some way, according to the nativist account, right? There is a way for a human to see or experience is see a set of things, 7 things, and represent 7 things in their minds without language. If they can do that, right, they should succeed at this task, right? But they don't. They only succeed for numbers that they can count to. And so there's nothing about this matching task that sort of like a priori requires counting, right? We don't tell them to count. We don't count for them. We're not using any number words for them at all, right? We're just, here's a set of things, make a set that has the same number, do it however you want. And so I think that some people have talked about, well, maybe they have the concept of 7, but they just can't access it for some reason. And I don't know if that's exactly what you're saying, but that's
I wouldn't have said that they can tell that there's exactly 7 here. That's not what I think one would claim. The question I thought other people were asking, though, and Mike Frank spoke to this issue a little bit and raised questions about whether you could make conclusions about it in his papers, whether they kind of even get that there is such a thing as an exact, they don't, the idea would be that you don't appreciate that there's an exact quantity, whatever it is. So for example, you could, even if you don't know how many are in a set, you could ask somebody the question, well, if I took one away from this and put a different one in there, would it be the same number I had before or not? Yeah. And if you can answer that question, then you may, but some of these people can't answer those questions as well, right? So that all, I guess, speaks to the general question of the nature of what they understand.
Yeah, well, with regard to that question of understanding exact numerosity, I think it's clear that these guys do. I lost my video for some reason, but I assume you guys can still hear me.
Yeah.
Yeah. I think it's clear that these guys do, right? So first of all, they all succeed on the parallel match task up to 15, right? So if you give them a set of 15 things, regardless of how high they can count, they can exactly match them up to 15 at least, and I'm sure beyond. And lots of these participants are making exact matches even in the orthogonal task, right? So you give them 7 things or 10 things even, and they will, without being able to match them one-to-one, make another set of exactly 7 or exactly 10. So it's clear that they understand, I think it's clear that they understand what we mean when we say make these the same, right? Make these have the same number. So I think that is sort of that is like answered here. And then the question beyond that is, well, that's not sufficient, or that isn't sufficient to be able to represent a specific set, right? A specific number. So I think these data sort of speak to both questions, right? Like, what is it? Are those things separable, right? Like, can you understand exact numerosity as an abstract thing? And the answer is without being able to represent, an exactly 12. And the answer is yes.
And I respond to that also. Frank et al. In their paper actually took up that question and said they do have a concept of it, and this is the Pitt who are much more sort of dramatically without an official language system than the Tsimane.
Yeah.
They do have a concept of exact number. They just don't have they said cognitive technology or toolkit.
Yes.
They don't have the tools to actually manifest it. And I think that seems to apply very well to the Tsimane. I think it might also apply to the Nicaraguan home signers who are in a numerate culture, and they're surrounded all the time by friends who pay for things and get change and so on. And they do okay on some tasks, but as you know, they start failing when the numbers get large. And so that really seems like a technology problem. But I'm not so sure with the Piraha. The things like that they count differently going up versus down. That's a pretty thematic.
Yeah.
Now that you could call that just technology, that they're just matching the language to the number, but I think it's at least an open question whether that's a more profound difference.
Yeah, I think this, I don't think we have time to, I'm curious to follow up with this, but just quickly, if I may, the question I want to flag in response is, what is the difference? What do we mean by cognitive technology? To me, it strikes me as a really nice poetic metaphor for concept, right? For like representation, for like the ability to remember across time and space some information. And that we can talk about that as a technology, but I'm not sure how it differs in any important way from conceptual representation. And maybe it does, but that's a question I would have.
Let's take it up in the breakout. I think that's a great topic for discussion.